Let's talk about parametrizing a curve. All that means is we're going to take a curve either in 2 dimensions or 3 dimensions and write it as either a single vector valued function or a group of vector valued functions. Generally we call this, as when we got a bunch of pieces, as a piecewise smooth curve, but we'll see what that means in a second. So let's take some odd looking curve here. Let's say, let's make it easy. Let's say that our curve looks like this. We start at the origin, we head over to the point 1, 0, we head up to the point 1, 1, and then let's say for fun we go back to the origin. So this is our curve C that we're going to find. Now when we see a curve like this, it's pretty obvious to see that it's made up of several different pieces. So let's call it C1, C2, and C3. Where here, our original C is made up of C1, C2, and C3. All right, so since it's distinctly 3 different pieces, it would be helpful to parameterize each piece of this curve. Now, since we're going to do a vector valued function for each one of these, let's say for C1, our vector valued function R of t is going to be equal to. We want to draw this piece right here. Now we need to decide what we want our parameter to run from. And of course our parameter here is t. Since x runs from 0 to 1, it may be useful to let our parameter run from 0 to 1 as well. So if you can see on this curve, what does x do? Well, x just travels linearly in the x direction, so that would be t in the I direction. Now notice x will run from 0 to 1 now, plus, and when we're on C1, the y value is always 0, so that will be 0j. All right, so that would parameterize the first curve C1. Let's take a look at C2. Now most textbooks here are going to want you to define this whole thing as what they call a piecewise smooth curve, which means that your parameter has to be continuous, which means the next parameter should start at 1 and go to something else, let's say 2. You actually don't have to do this, except for you're trying to prove some theorems, which this makes it very, very helpful. You don't have to have any connection between these parameters to make this work out. So let's call C2. Again, notice the y value runs from 0 to 1 here, so it would be helpful to, again, let our parameter run from 0 to 1, which we'll see that's pretty useful in a lot of these. So anytime we're on C2, our curve R of t will be, well, 1 in the x direction, right? For every point on this curve, x is 1. And in the y direction, we just go up linearly, so just t. So this should describe every point on C2. All right, let's take a look at C3 and see if we can describe this parameter. Now again, notice we go from the point 1, 1 to the point 0, 0. So we got zeros and ones. So again, it may be a really good idea to run our parameter from 0 to 1. Okay, so what does the x do everywhere on this curve? Well, the x goes from 1 to 0, so it kind of wants to run backwards. Now, we generally don't run our parameter backwards. We don't go from 1 to 0, even though technically you can. So how would we make that work backwards? Well, it's always going to be something like this. We want it to go 1 minus t in the x direction. Notice when t is 0, x is at 1, and when t is 1, x is at 0, so it moves this backwards. Now, we're moving along a line, so we want that to be linear. We also want it to be linear in the y direction, and we want it to do the same thing. So notice this will now run from the point 1, 1, when you plug in 0, to the point 0, 0. Since they're both linear, we're going to be moving along a line. So parameterizing a curve is something that's going to be required a lot in the rest of this chapter. Let's take a look at another one just for practice. One that we may use in our upcoming examples. Let's take a look at our curve here, C. Let's say we go like that. Again, let's go to the point 1, 1 just to make it easy. Now, along this curve here, that's going along the parabola y equals x. In this curve here, we're going along y equals x. And let's say that we went around this way. So the idea for this curve C here, we're going to start at the origin, we're going to go along the parabola until we get to the point 1, 1, and then we're going to go back to the origin along the line y equals x. So hit pause real quick, see if you can parameterize this curve C. All right, if you're back, let's see what you did. So let's name these real quick. Let's call the parabola part C1 and the line part C2. So our curve is made up of C1 plus C2. So we need two pieces to parameterize here. So for C1, R of t is going to be equal to, well, again on C1, notice that we run from 0 to 1s here, so it'd be a good idea to let our parameter go from 0 to 1. Right, what does x do? X just goes from 0 to 1 here, and you can think about that as a linear direction, but the y is going to run in a quadratic direction. So this would work if we let x be t and the y be t squared. Now how do I know that that's t squared? Because along this curve, whatever x is, y is that thing squared. So we let x be equal to t, so the y part had to be t squared. For the second part of this, r of t, we're going from point 1, 1 to 0, 0 along the line y equals x. I think we just did that on the last one. So let's see, that should give us 1 minus t in the x direction, 1 minus t in the y direction. Okay, so there's the parameterization of this curve. You don't have to make it piecewise smooth like the book necessarily says, but since I'm saying that you don't need to do this, these parameterizations are not unique, which means there's more than one way to parameterize these curves. It means that your answers may differ from the back of the book from time to time.